have the binary tree post-order traversal here. We'll do it in two ways. First, the quicker way, the recursion, and the second, the iteration way. It will give you a better understanding of the inner mechanism of binary tree. Let's start off doing the recursion way. So just a recap. So post order is where you access left, right, and the current node. So result equals to this, and self dot will make a helper function and return result. And the helper function we name it post order and self root and result. And so for exit statement, so if root is none, we'll return none. And first we access left, so it'll be self dot post order root dot left, and same for result self dot post order root dot right, and the same result. There's an extra parentheses here. And lastly, we append the root value. Since we want to return the value, so we'll append the value instead of node, and that should be it. Submit. It works. So as for space complexity, it will be O of n being the number of nodes in the graph. And for time complexity, since we have essentially we just go through every single node in the graph, so it will be O of n. And then let's go to the more challenging part. That would be the iteration. So we want to do an iterative approach. Then we have to have a good understanding of what is actually going on inside of a post-order traversal. So for example, the graph right here. So once you're here, and instead of visiting this node, you want to first prioritize its left node and then its right node. So if you're here, you want to make this jump from the left child to the right child. And we will adopt a stack here because we want to have the last in first out property. And let's see how we will handle this problem. So let's do a sanity check as always. So return empty if the root is none. Then we will call the stack route. So this is stack, and cur equals to root, so just to keep a copy of the root. So first, what you want to do is have the original trail, original route, if you might call it. So for example, in this problem right here, we want to first record this node, this node, this node, and this node. And if this node doesn't exist, we'll record this node, this node, this node, this node, and this node. And the reason why I want to do that is because if we don't have this node right here, let's say it is cut off from here, these in the reverse order, which will be provided by the stack, is the first to be printed out since they don't have the left child and a right child. So this guy will be printed out first since it doesn't have a left child or a right child, and it's sort of on the bottom leftmost corner of the graph. And once this is out of the way, you can see this follows the same property as this guy. It doesn't have left child and right child, and is on the leftmost corner of the graph. So by getting this route, we can sort of anchor ourselves to where to start. And then, so while cur route.append cur, and if cur.left, cur equals cur.left, and elif cur.right, cur equals cur.right, and else we break. And the reason why we prioritize the left node, because obviously if this guy is still here, the original route will be this, the left former nodes. And we will use a exclusive if and else if, since we only need one route. We don't need both sides, we only need the left, sort of figuratively, the leftmost route. And once we reach a point where it doesn't have right child or left child, we just break out as for loop, and that would be our original route. And then let's move to the actual building part. So essentially the idea is, so now we have this route to anchor ourselves on. So it will have this guy be the top of the stack, and we will of course record it first since this is the first value. So let's say we already have this in our output value, and now this guy is on the top of our stack, but this is not our next value to be outputted. It's this guy or its children. Then we want to make this jump right here, and the way we're gonna do that is first we check the top of the stack, which will be stack -1, and we see if its left child is the current node. If it is, means that the current node is the left child of the top of the stack. Then we will make this jump, and we'll want to access stack -1 dot right. That's how we're gonna jump to the right child. So we will have this left, right, then mid property as required by PostOrder. And let's see how we do that. So while there's stuff on route and our output, we'll name it order. First, we'll pop the node. We'll call it cur, so route.pop, and we'll append it to the order, since like we mentioned before, this guy, if it's on top of the stack, is guaranteed to be outputted first. So we add it to the order. And then is when things become a little bit tricky. And like we mentioned before, if there's still stuff on the route and the top of the stack, if its left node is equal to current node, that means the top of the stack is the parent of the current node. Then we don't want to visit it. Instead, we want to visit its right child. So cur equals to route -1. This is the parent dot right. And now we'll follow the same process here, since we want to find a optimal route. So for example, we just get done with this and we jump to this right node here. And in this guy right here, we will follow the same procedure as go to its child, left child, right child, and same jumping. So while cur and route that append cur. So essentially we're doing the same thing. So cur dot left, cur equals to cur dot left, and elif cur dot right, cur equals cur dot right, and else we break. And if the current parent doesn't have a right child, you can see it would just simply never go into the while loop. And once we're done with all this, we can just return all order. And let's do a quick recap with this graph on the side. So first we do a sanity check, and then we create a route stack. So we want to anchor ourselves to some stack we can base our traversal with. So we'll get the, figuratively speaking, the leftmost route. So if this guy's here, it will be 1, 2, 3, 4. If this guy isn't here, it will be 1, 2, 3, 4, 5. And if this tree isn't here, so it'll be 1, 2, 3. So we can just keep cutting. And if this guy isn't here, so there's only these 4 nodes, it will be 1, 2, 3. So it'll be this guy right here. And now you get the route thing. Then we initialize our order output value, and since the top of the stack is guaranteed to be output, we add it to the output value. And now we're at the point we have to check if this is the left node of the top of the stack. So if it is, so if there's stuff on the stack and the top of the stack is actually a parent of the current node, we want to jump from the left child to the right child if there is any. Then we'll follow the same stack for the same strategy to anchor ourselves with a new route with the new right node being the root. And once we're done with all this, we should get ourselves a order. So essentially, we're just following the requirement of PostOrder, where you do left, right, then mid. So let's do a quick compile. So if it works, and let's try to submit it. So it works. So for space complexity, we introduce one additional structure here. So it'll be all of n, as in the worst case scenario, we will have the route being the entire thing. So it will be all of n, given n is the number of nodes. And for time complexity, for here, we're just doing all of n scan, as the worst case scenario is we just put everything on there. And for the route, we're just essentially going through everything on the graph. So worst case scenario will also be all of n. So the overall time complexity will be all of n. So just to recap on this problem, first, we need to realize what is the essence of post-order traversal. So basically, you want this left, right, mid property. So if we're at a potential left node, we want to check if it's the left child of a parent node. And if it is, we want to make this leap right here. And the way we're going to execute this jump is this line right here. And once we get this idea of jumping and the original anchor idea, this question is rather simple.